Today's video is about a question that's been on my mind for quite some time. The question is this: suppose we have a pair of entangled photons, one is blue and one is orange. They're entangled in terms of polarization. So, when one is measured to be horizontally polarized, the other is also horizontal. When one is measured to be vertically polarized, the other is vertical. This can be represented by a Bell state, which you can see here at the bottom right corner of this virtual lab. By the way, this virtual lab is called Quantum Flytrap. It's free and really fun to explore. Now you might ask, what am I trying to do with this setup? Well, the goal is to disentangle the photons so that the state of one photon becomes independent from the measured state of the other. But here's the twist. I want to do this without collapsing the superposition. Let me explain what I mean. If I put a linear polarizer in the orange photon's path and it gets absorbed, then yes, the photons are no longer entangled. But the superposition is gone too. Even if the orange photon passes through, its polarization is fixed, so the system is no longer in a superposition state. What I want is different. I want to disentangle the photons but still keep the superposition, at least for the blue photon. So here's the process I'm testing. First, the orange photon hits a polarizing beam splitter, PBS. If it's horizontally polarized, it goes straight. If vertically polarized, it gets reflected. Since the photon is in a superposition of H and V, it takes both paths. Next, in the reflected path, there's a sugar solution that rotates its polarization by 90 degrees, turning it from vertical to horizontal. Meanwhile, in the straight path, there's a piece of glass that adds a phase shift. Now both branches are horizontally polarized, but still in different spatial paths. Then, using mirrors, I bring the two paths back together. One path gets an additional glass plate to match their phases, so now both parts are in phase, horizontally polarized, and traveling toward a merging point. At this point, I don't have a physical element in the virtual lab to merge them perfectly, so I represent it with a Y-shaped waveguide in my PowerPoint slide. Here comes the key question. What happens to the quantum state after the two paths are combined? Before combination, the state looks like this. The only difference between the two branches is the direction the orange photon is traveling. One is right, one is down. So I'm assuming that after combining the paths perfectly with matched phase and polarization, the two directions become a single mode, aligned with the waveguide output. If that's correct, then the quantum state becomes this. Now, because the prefactor and the orange photon's ket are the same in both terms, I can factor them out. And what's left is a product of two independent states, one for the orange photon, one for the blue. This means the system is no longer entangled, but the blue photon is still in a superposition of horizontal and vertical polarization. And importantly, the interference pattern isn't obscured by a minus sign or a phase shift. We expect a clean interference. Now, let me pause and be very clear here. This conclusion is based on the assumption that combining the two spatial paths into one mode effectively collapses the orange photon's spatial superposition without destroying the polarization superposition. That's the hypothesis. I'm not certain this is physically valid, and that's what I'm exploring. If it is valid, then that means Alice, on the orange photon side, can do something like inserting or removing the recombination setup and affect whether Bob, on the blue photon side, can observe interference, which raises interesting implications. But again, this only works if the recombination truly leads to disentanglement without collapse. So, what do you think? Does this make sense? Is my assumption reasonable? Or did I overlook something critical? Let me know in the comments. Thanks for watching. See you in the next one.